Hello, everyone. Excuse me. Hi. Hello, everyone. So today I'm Fatima and my colleague Amar. We are professors at Vistava student, and we are going to present today's lecture. And it would be going to be about, we're going to talk about different sources of time provided by an embedded platform maintained by an operating system, and how you can use different sources of time and different sources of clock provided by your operating system in different user space applications. So I'll start first, and then in about half time, my colleague Amar will take over. So what do you think of when you hear about clocks? What are clocks? So a clock can be a hardware entity like an oscillator or a counter. And the deep down in the hardware, a clock is provided by an oscillator that ticks at a nominal fundamental frequency. And this is the core source of your clock, which is periodic in nature and is actually providing you the periodic oscillations. And then the second part of this is actually the counter element, which is responsible of counting the oscillations provided by the oscillator. And then in the software, a software maintains those counts. It actually takes those counts and converts it into a human readable or understandable form, which is in seconds. Okay? So whenever you hear about clocks, it could talk about any of these elements in the entire timing stack. We call all of these blocks bunched together as part of the timing stack. So clocks could be a hardware oscillator counter, it could be software abstractions maintained in the software, or it could be logical clocks, which are just mathematical models representing a periodic source of tick and some human understandable form of time. So we're going to focus on different kind of clocks that the Linux operating system provides. And all the other operating systems like Windows and Mac, they kind of follow the same approach which the Linux provides. So how does the Linux timing stack looks like? First, in the hardware, you have these hardware counters that are getting their fundamental frequency, or basically the tick, from the oscillators. In the hardware, you also have a bunch of registers. Those registers are responsible for many things. First, they can load the initial count value in the hardware counter, like where would you start counting from. It could also provide the value at which the hardware counter should provide an overflow signal. So let's take an example. So suppose you have a hardware counter that has a width of 16 bits. After how much time would that, if that counter starts counting from 0, after how much time would it overflow? It's a 16-bit counter, it starts counting from 0. After how many counts or after how many ticks would it overflow and wrap over to 0 again? Yeah, 2 to the power 16, which is 65,536. Now, all that hardware counter is providing is that starting from 0, 1, 2, up to 65,536. So what happens afterwards? It overflows, and then it wraps back to 0. So how would you take this particular hardware counter with a known frequency provided by the oscillator and convert that to a human understandable time, which is in seconds? Because it's constantly wrapping over, it's constantly overflowing. So you need to make use of that information to actually maintain a human understandable form of time, which is in seconds. Any idea how would you do that? Yeah. And where would you maintain that counter? You're right, yeah, you're right. So you would actually do that in the software. You would actually keep track of those overflows that the hardware counter is overgoing, depending upon when you actually started the hardware counter. What was your main epoch time, the time when you actually started that? Okay, so time is not a very simple thing. It builds upon layer, and then you get what you see in your laptop and in your mobile phones, the time which you're able to see. but the fundamental source of time is coming from the hardware oscillators and the counters, and they all share the same features, that they have registers and they go through overflow. Oops, other way. Okay, so and one more important characteristic of that oscillator is that it has a certain frequency stability characteristic. Let's suppose the oscillator frequency is 1 megahertz. It may not necessarily oscillate at 1 megahertz. It may oscillate due to some hardware manufacturing uncertainties. It could oscillate at 1.111 megahertz or like 0.99999 megahertz. And that source of error it actually translates into the frequency stability characteristic of the oscillator. And if you see this graph, these lower values correspond to a better frequency stability and a better oscillator. But you see, the lower value you get, the more price and the more power you have to pay in terms of the oscillator. So most of the embedded platforms that you have, Beagle Bone Black, Raspberry Pi, they mostly have that quartz crystal oscillator somewhere over there. That's pretty cheap, take less power, but it's very unstable. Its frequency stability characteristics are not that good. Okay. Move this power. This power? Yeah, sorry. 1 milliwatt. It's watts. Yeah. Okay. So you take that hardware counter value and now you have to represent it in seconds. Basically, Linux operating system maintains in nanoseconds. And what sort of software abstractions that the Linux kernel use? It uses the clock source software abstraction in the Linux kernel, which is nothing else except a wrapper around the hardware counter, some underneath hardware counter. And then it uses some kind of timekeeping functions, and I'm not going to go into details of these. And then it uses the POSIX clock interface, which is a very standard Linux interface, and it is actually responsible to expose a virtual clock to the user space application. So now what the user space application see is not all this, what I've just explained. What they see is that they have a clock, name or the ID of the clock is clock real time, and the way to access that clock is through the API which the Linux kernel provide. The kernel provide get time, set time, adjust time, get resolution of the clock. So these are the API which you get exposed to, and you can manipulate the clock or read the clock. And this clock real time, this clock ID in Linux operating system corresponds to the system clock. So whenever you have a Linux operating system and you just write get time, this is the clock which they are getting the time from. So what are the characteristics of this clock? So clock real time, it's a system-wide clock, and this is the time that's being used by all the applications running on Linux. And its approximation of time is in UTC time, which means that the epoch, which means that the starting point of this time is 1st of January 1970. And they maintain the UTC time. And a user space application has control over this clock in terms of it can jump the clock or it can slew the clock. Slowing the clock means I can change the frequency of the clock. So if, let's suppose you have another clock source which is more stable and accurate, you can synchronize your Linux clock real time with that more stable clock by either jumping this clock or changing the frequency of this clock. Yeah.
If your device isn't connected to the internet or anything, how does it know?
It doesn't. That's the only way it knows. Some external, more precise source. Or maybe you have a device, you've connected it to GPS. That's another source of getting a good external accurate time. Of course, you can set it once, which is like jumping it once, and then later on, very slowly and carefully changing the frequency and then manipulating it that way. Most of the synchronization protocols, they jump the clock only once, and then they play around with the frequency so that the time doesn't drift apart from the external time. Okay, then you have clock monotonic. The hardware layer, the oscillator and hardware counter, they are the same for clock monotonic, except that they are maintained in a kernel in such a way that you cannot jump that clock. You can only change the frequency of this clock. The reason for that is that certain applications, they need a monotonic source of time. Monotonic means that the clock should never go back in time, which can break the functionality of an application. So they have restricted this clock that you cannot jump it. You can only slightly change the frequency characteristics of this clock. And then the other clock which the Linux provide is the clock monotonic raw. The hardware counter and the oscillator for this is again the same, but for this you cannot, you don't have any kind of control over it. This is a very precise clock. This is basically returning you the hardware counter value multiplied by the frequency to get some certain nanosecond, and this is what it provides. You cannot change the frequency of it, you cannot jump it. The main purpose of this clock is to keep track of very small and precise intervals. So you do get time before the event, you do get time after event, calculate the difference. That's what this clock is used for. Any questions so far? And then these are the standard API you see in your Linux operating system, clock get resolution. You mention the ID of the clock you want to use, and then the value where you want to store it. You can do get time, you can do set time. You can do set time only on clock real time, not on these two clocks. So these are the different API in your Linux operating system that you can use. Another set of API is get time of day and set time of day. And you see over here that you have not provided any sort of clock ID over here. So which clock do these API use? Any idea? Yeah, this one, the clock real time. Because this is the system clock provided for your Linux operating system. Get resolution of the clock. Resolution is the width of the tick. For example, if it's a 1 megahertz clock, the frequency is 1 megahertz. 1 over 1 megahertz is 1 microsecond. So the resolution for that clock is 1 microsecond. It's the width of one tick, yeah.
Does that also return you the
No, it's not giving you the PPM oscillator. For most of the platforms, the PPM of the source of information of getting the PPM for your particular oscillator on your platform is the data sheet, because it's a hardware characteristic that only the manufacturer can tune and specify. But you can do different experiments and measure the PPM analytically as well. Okay. So this was your clock real time, but that's not all what you have on your embedded platform. This is the normal system clock which you are exposed, which the applications are exposed to when they don't have any information of any other clock on the system. But it doesn't mean that we don't have any other clocks on the system. Recent embedded platforms, they have this another clock source which we call as the PTP clock. Now, why do we need another source of clock when we already have the system clock? The reason why we have is the PTP clock is that it's a much better precise clock. It's called precise hardware clock. The system clock, it's not a hardware clock. And I'll explain what a hardware clock is, what a more precise clock is later on in the slides. You'll get to know what's the difference between them. But the system clock, it's not that precise. And then there are certain applications that need a precise hardware clock. And then they follow this separate path in order to get the precise hardware clock. You see that maybe they would be sharing the same counter, or maybe they have a separate counter in the hardware, or maybe a separate oscillator. But they may share the same oscillator or hardware counter as well, depending upon what platform you're using and what kind of specification it has. Anyway, so the precise hardware clock in the kernel layer, it uses these two software abstractions, the cycle counter and the time counter. The cycle counter is just a wrapper around your hardware counter, and the time counter maintains the nanoseconds, converts the cycles given by the cycle counter and the hardware counter, and converts that to nanoseconds, depending upon what the frequency of your oscillator is. And then some other things too, which I'll explain in the next slide. So you get, using these software abstractions, you get this PTP clock abstraction. What PTP clock is that it's just a POSIX clock, and what POSIX clock is that you have to implement these API. PTP clock also implement those API, the get time, set time, resolution, all of that. Plus, it also gives an extra set of hardware pin functionalities. What I mean by that is that suppose you have an embedded platform, it has many I/O pins. You can specify which I/O pin would you use for this particular clock. You don't have that kind of functionality with the system clock. So what will happen if you have any kind of event on one of those I/O pins, this clock, this PTP clock, can timestamp it very precisely in hardware, and also vice versa. If you want to generate a very precise event in hardware on some of the pins, that PTP clock, based on the PTP clock's time, you can generate the event on a particular pin. So that would be very precise. If you say that I want to generate a precise event at some seconds and few nanoseconds, it would make sure that it generates the event on a particular pin at those exact, not that exact, with a little error of nanoseconds on the hardware pin. That's how accurate it can get. But it also depends upon what sort of hardware characteristics, the specifications you have. If you have a higher megahertz clock over there, only then you can reach the nanosecond precision with the PTP clock. And that PTP clock also gets exposed to user space as a character device, which you see, dev PTPX. X could be 0, 1, 2, 3, any number. And the user space applications can open that character device and do file operations and use some kind of I/O control calls or different pin capabilities to actually make use of that. Yeah.
So if you're saying it will have to get time at that time,
it has all of them.
what's the point of maintaining the POSIX clock then?
POSIX clock is a system clock which you can just do. Okay. So over here, get time, set time, whenever you specify that, you have to give the clock ID as well, right? And you'll get the system clock time over there, right? Over here, you also have to do something similar, except that now you also get the hardware pin functionalities, the precise hardware time stamping and event generation capability with the PTP clock as well. If you don't need that, you don't need this clock. You can only work with that, right? Oh, what you're saying is, why can't we just use this?
Yeah.
Why do we have this? Because this capability requires certain hardware functionality which not every platform has. It's not present in every platform. It's present in some of the embedded platforms, some of the desktop-based. Yeah. No. The both paths are completely separate. Yes. They don't have anything in common in terms of this path. It's just that this is kind of like a Java concept. It's extending this class, and now it has to implement the methods provided by this class, something like that in the programming. This arrow is only for programming purposes inside the source code, nothing else. So just to be clear, not every platform has the capability of a PTP clock. Since in your class you're going to do some kind of assignment, and I think professor wants you to be familiar about this precise clock as well, so we're going to choose a platform which has that. So not every platform has that, but every platform has the system clock. Yeah.
If they both come from the same oscillator, how could that one be more precise?
They may not necessarily, but if they both come from the same oscillator, this is precise because there are certain pins on the hardware platform that are directly connected to this counter. If they are directly connected to this counter, what you can do if you want to timestamp a hardware event at a particular pin, as soon as it arrives on the pin, and that's still in the hardware, this value gets captured in one of the registers. Yes. This may not have that. Not every platform may have that. You need those hardware pin functionalities to implement this. Otherwise, you don't need this. You have this. Okay? Any other question? Okay, so let's see details of this PTP clock. So there's a synchronization protocol where you synchronize a local time with some external, more precise time, and that's called precision time protocol, and that's where this clock gets its name from, PTP clock. I'm not going to go into detail of the synchronization protocol. I'm not going to talk about synchronization at all in this class, but it has the hardware time stamping capability, which I've just explained. Just to elaborate the difference between this one and this one, let's see which path they both will take for time stamping. Let's suppose an event occurred on a pin, right? What happens when an event occurs on a pin? An interrupt occurs, right? So this system clock can capture that event at maximum in the software, cannot capture that event in the hardware. The difference between this path is, for the same event on some pin, this path can capture that interrupt in the hardware. So the lower you can capture, the sooner and faster you can capture a hardware interrupt, the more precise it is. So this can capture that interrupt over here. This path can capture it somewhere in the kernel at best. That's why you get a precise reading of your timestamp from that PTP clock path, because it has configured the pins, the hardware pins, in that particular way. Yeah. Okay. The concept of this PTP clock is very useful, and it's used widely for the network interface cards, for the radios, for, let's suppose, for Ethernet. The Ethernet controller was the very first subsystem that actually implemented the precise hardware clock. What it does is that whenever a packet enters the Ethernet subsystem or leaves the Ethernet subsystem, it timestamps that packet very precisely in the hardware. But it doesn't mean that it's only fixed for NICs. It could be used for other clocks as well, not just for packet exchange, but mostly it's used for that. This is how it's look like in the source code inside your kernel. So this is the structure. What you have to pay attention to is these set of functionalities. How many number of pins you have, whether you can produce a pulse per second, precise pulse per second signal on your pin, whether you can externally timestamp a signal on a particular pin, whether you can produce a periodic output on a particular pin. So these are the pin functionalities with this PTP clock has. If you just remove this, all of this which I've highlighted, then this is the same as that would be the same as the POSIX clock interface. And if you insert these functionalities along with the POSIX one, then it would become the PTP clock. Yeah. That's a hardware characteristic provided by the manufacturer. And these are the necessary functionality which every POSIX interface should implement. And PTP is also POSIX, so it should implement that as well. Okay. So one thing more about this PTP clock is that if you can timestamp an event in hardware, you can also discipline the clock in hardware through its registers. And then again, not all clocks provide that feature. There are, the Beagle Bone Black platform, which you're going to use in this class, it doesn't have that feature. But just to let you know that there are certain platforms that have, I don't know any right now, but there are certain platforms who have this feature where you can program the hardware register values to control the frequency and the time of that particular clock. Of course, for this kind of functionality to happen, you should have a separate hardware counter or a separate oscillator for this path if you want to discipline that in the hardware, right? And then that's not it. You also have another source of clock on your platform, which I call a peripheral clock. What this clock is, suppose you have a subsystem on your platform. It has an oscillator, it has a counter. For a clock, all you need is a hardware and oscillator, and then you can write the software yourself to maintain it as a clock. So suppose you have a subsystem on your platform. It may possess certain kind of functionality that you can do memory map I/O to actually expose the registers in that particular subsystem hardware and expose that to the user space through UIO. Then what you have to do is that whenever, suppose a hardware interrupt occurred at that particular subsystem, you store the value of your counter in a register, and that's automatically exposed to the user space by bypassing the kernel in the user space. You have that value. I mean, of course, that value is a count value. You still have to change that to a nanosecond or a second. But you also have this path of completely bypassing the kernel and directly playing with the registers in the hardware by sitting at the user space. Is it confusing? That's called user space I/O or a memory mapped I/O. It's a very strong concept in the Linux operating system. You map the memory and the registers in the hardware directly to user space. So now the application have access to the registers. I think this is similar to what your microcontrollers do, right? Your microcontrollers, they don't have an operating system. What you can do is directly write to the registers and read from the registers. This is something similar. Okay? You bypass the kernel. You have that functionality on a platform as well. Beagle Bone Black is one of such platforms. It has a main processor which has Linux running on it, and then it also has a small, you can say a small coprocessor which doesn't run the Linux operating system. And you can do something like that to get even more precise timing characteristics using that coprocessor. Okay. Any questions here? So these are the three distinct clock types which you may have in a platform. The middle path, you'll get it on every platform, desktop, embedded, whatever. This path, you'll get on certain embedded and certain desktop platforms, which actually supports that. And that's much more precise if you want to timestamp hardware interrupt. This is much more precise than this one. If you're getting a hardware interrupt somewhere in the hardware and you're timestamping it up in the software, it would be too late, and you'll not get a better precision. If you're getting a hardware interrupt over here and you're timestamping over here, then you get a better precision. Same for here. If you have an event occurring for a peripheral clock somewhere here and you're timestamping that in the hardware, you have a very precise clock. And I think in one of your programming assignments, you'll actually compare all of these clocks, all of these three different clocks, and see what sort of timing accuracy you get for your hardware events. Any questions so far? Yeah?
Is it possible to have multiple oscillators the same exact time that you somehow like average their time and get a better signal? It's like in a lot of the systems that don't have access to internet or any way to check their clock, those drift over time. So over the course of a few weeks, they can be really, really long. Is it possible to get like for a certain BPM rating, you get 4 of them, let's say, and you have to basically compete against each other?
So it depends. There are many ways of doing so many different things, but it depends what you ultimately want. Why do you want to get a very precise time on a single platform? Okay, let's suppose you have two different platforms. They may have to do some certain task at the exact right time, right? This is the scenario which you want, let's suppose. Do you understand my example?
I was just talking about one.
For one platform, the best you can do is to get the same clock for all the different applications that need time, right? If they're using a single source of time, their time would be the same, right? Most of the time, synchronization problems occur in different platforms. If there are two different platforms with completely different sense of time and they want to do something at the same time, then you need to synchronize their clocks, right? And then if both of those platforms, they have some certain oscillators, like a quartz crystal, who has a very bad frequency stability characteristics, then their frequency would relatively drift with respect to each other, maybe in the exact opposite direction. Then you need to constantly synchronize both of those clocks through some packet exchange and other mechanisms. Either hook both of those platforms through GPS, get a common signal from GPS, or maybe do a packet exchange among those two platforms with their time information. So that's a completely different subject. But if you have a single platform, just take a single source of time. Take a single clock for both of those applications. Okay. But a single platform can have multiple oscillators and multiple counters. Beagle Bone Black, again, the platform you're going to use for this clock, it has multiple oscillators and it has so many timers. That's why we're using it. So you can play with different timer capabilities it has. And it also has this coprocessor kind of thing, this path, which you can also use. What time is it? Wow. Okay, so this is just a side note slide, which you can later on, when you get a hold of these slides, take a deeper look into it. But all it's telling you is that how complicated it is to get a cycles value from a hardware counter and convert that to a nanosecond value. Well, you think that, okay, you have a cycle value, just divide it by the frequency of the oscillator, and that's how you'll get time. But it's not that easy, because you do all sort of those calculations inside your kernel, and the kernel do not support floating point operations. So you have to do all through shifting values, shift registers here and there, calculating different values, maintaining the fractional part of your value, and then adding that back in your nanoseconds value. So it's actually not that simple to convert your cycles into nanoseconds. And this is the kind of math that they use. You can later on take a better look at how they do that, or maybe ping me if you don't understand what's happening there. And then over here as well, this particular piece of code, what it's doing is that it's accumulating time. Like I mentioned before, that you have a hardware counter which overflows after every, depending on what's the width of the counter, every 2 to the power 16 bits or 2 to the power 32 bits, whatever the width of your counter is. So you need to make sure that you accumulate time before it overflows again, right? That's what this code is doing. It's taking your cycle values, current cycle values, converting that to nanoseconds, adding that back into the previous nanoseconds value, and doing that at least once for one overflow period, so that you don't miss one overflow and you maintain time properly. Even if you miss one overflow, depending upon your frequency, you're off by few seconds, which is not right. For some applications, you need milliseconds or nanoseconds precision. So this piece of code is very important. Anyways, any questions in that? Okay, now that you know different sources of clocks in your operating system, in your embedded platform, let's see how would you do time stamping with those clocks, because that's why you have clocks for. Get a precise time value through time stamping. So this is how a regular Linux operating system looks like. You have hardware, counter, resistor, oscillator, you just saw that. You have a driver, depending upon what subsystem you're using. Let's suppose, for the time's sake, we're using a network interface controller. It could be an Ethernet controller, it could be any wireless radio, okay? I'm taking an example of the networking for packet exchange right now. You have a hardware, and then you have a driver for that particular network interface controller, a NIC, and then you have these set of libraries maintained in the kernel that are actually going to help us, a set of libraries that are actually going to make things easy for a packet which is entering in the hardware to make it reach the application. And then finally, in the user space, you also have a set of API that makes things easy for you. And you don't have to go through block by block to understand what's going on. The purpose of this is that, let's suppose a packet entered your Ethernet subsystem, it timestamped that and stored the value in a register. What happens is that as a first step for a user space application who's interested in that timestamp is to tell the hardware, that Ethernet subsystem, which specific packets that it has to timestamp, right? Since it's the hardware that's timestamping the packets, the software should tell them which packets to timestamp so that it doesn't timestamp all the packets. That's a very big burden on the system. You cannot timestamp all the packets. You have to specify which packets you're interested in timestamping in the hardware. Once you tell them, and then the hardware timestamp the value, store in the register, what to do with that value. What we need to do is that take that value and send it to the user space. That's what we want, right? Because the user space is going to make use of that information. So the driver is responsible to copy the capture timestamp from the register, and then the socket is a networking stack data structure that you actually use, and the socket is basically used to, it's part of the networking stack in the Linux kernel, and the responsibility of the socket is to take the protocol data unit, the data part of your packet in the network, take that from the hardware up the stack to the user space. So we're going to use the similar socket, not just only take the data packet up the stack, but also take the timestamp value of that data up the stack. And then you use the regular Linux receive message API to actually receive both the packet data and the timestamp. This is just the overview of how you take the timestamp from the hardware up the user space using the kernel subsystem. Which delays? All of those delays, but okay. The point is that whenever a packet came, you timestamp that and you store that value in the register. Now, even if it takes so much time to take that value up the user space value, it doesn't matter because you've already timestamped that at the right moment and you already have that value. Now, if you choose to process it later with certain delays, that wouldn't change the fact that you got the right value. Does that answer your question? Of course, it would take time to actually take the value from the register, copy that to a socket data structure, and then using some of the API to read that in the user space. There are two things that are important for timestamping a packet. Whenever a packet enters, you timestamp it instantly in the hardware. Number one thing, that's important. The other thing that's important, that you put that timestamp value to the same data of the network of the packet to which it belongs, right? You don't append the timestamp value to the next packet. You need to append that to the same packet value. So all you have to do is to make use of the networking stack that's already established in the Linux operating system in the kernel, and then append that timestamp value in the register to the proper to the proper network packet that you sent up the stack. The thing is that all of this has been taken care of you. All you have to do is use the API, like receive message API, to get the right value. For Ethernet, all of this, what I'm talking about from the register, socket, all of that, that's already part of the mainline Linux kernel. You don't need to do that. Yeah.
So when you say timestamp, what format is it? Is it in seconds, or is it going to be a different value, or do we have to offset from the packet, like to other regions?
It depends which clock you were using, the clocks which I mentioned previously. Okay, it also depends upon that. But this register value, it's in cycles. Let's suppose when the driver copied it, now driver is going to copy that value in the socket buffer, okay? The driver can change the cycle value to nanoseconds and then send over there. It can choose to do that, okay? And then the socket can, yeah. And then the driver is actually responsible for selecting which clock it can use to, the 3 different kind of clocks that I've mentioned, which it wants.
So by default, these methods give you one kind of value, they give you cycles?
No. The next slides would actually come. Okay. So this is just the big picture, and I'm going to go into smaller things, but maybe I'm running out of time. Okay. So how does socket-based timestamping look like? This is exactly going to answer your question. The Linux operating system provides us two different kinds of timestamping. The very first one, this one. This attribute you use for software timestamping. When you don't have the hardware timestamping capability, your hardware is not capable of timestamping packets in hardware, then you use this software timestamping capability. And then this other one you specify for hardware timestamping. You also specify some certain flags to further elaborate what sort of timestamping you need. This TX hardware means that you are going to timestamp the transmitted packet in hardware. RX hardware means you're going to timestamp the received packet from someone else in hardware. This TX software means that you're going to timestamp the transmitted packet in the driver, just above hardware, not in the user space. That would be very bad then. This RX software, you're going to timestamp the received packet in the driver, just above hardware, which is not as good as hardware, but still good. And then this last flag means that you're going to read whatever timestamped hardware values you have in the user space. So these are the flags that you have to specify. All of these API, all of these flags is already part of the Linux kernel. Then in your user space application, you set this socket option. You specify the socket ID, which you opened, through which you are actually exchanging packets, transmitting and receiving packets. You will get from the socket layer, and this is the timestamping, this hardware timestamping is specified, and these are the flags, set of these flags what you want. Yeah?
I just want to mention, so the TX and RX in hardware, I think, are not available in the Raspberry Pi 3. I think someone was asking on Scout about using Raspberry Pi versus Beagle Bone.
Beagle Bone Ethernet has that.
Yeah, Beagle Bone does, but Raspberry Pi 3 does not.
Are you using Raspberry Pi in the class? Do you have an option? Okay.
Like, use that instead of Beagle Bone.
Okay. Yeah. Yeah. Whatever, I don't know what Professor Armani has set up. I don't know if they have given you the option of choosing any other platform. Most of the assignments are related to Beagle Bone, in my opinion. Yeah. And these characteristics that I'm explaining, timestamping a transmitted and received packet in hardware, Beagle Bone has that. Okay. So you use this set socket option API to actually specify that you need hardware timestamping, and this is the flags that you need. And then this is the setup part. The left side is the setup part. And the right side, now that you have set up, now the packets are transmitted and received, how would you actually retrieve the timestamp? In the big picture slides, some slides before, what I've shown is that now you have the value in the register. What you have to do is to take that value from the register up the stack to the application, right? And that's where you use this API, receive message API. And this is the same socket which you use to actually set up timestamping. And this is the message. This is the message which contains the packet, the entire packet metadata, and also control structure that is also assigned to it. And these are flags with a, okay. So this message also has an auxiliary control message data. And the reason why I'm mentioning this one, because it's very important, it's the exact data structure where the Linux kernel appends this timestamp information. And this timestamp is a timestamp array where TS0 is the software timestamp, TS2 is the hardware timestamp. And that's how you get a hardware timestamp in your message by calling the receive message API. Everything that happens underneath by taking the value from the register up the stack, copying it to the control message data of your actual packet data, that happens underneath in the kernel, and that's already done at least for Ethernet. If you want to do it for any other network interface card, you have to change the kernel code yourself as well, which I don't think you'll do in this class, but just for your reference. But all of this information which I'm telling you, that's already part of Linux documentation, is already implemented there. You can use it. Okay. Do you have any questions? I think that's it from my side. And then in your driver, which is just above hardware, you're going to specify which clock you're going to use to actually do that. And of course, if you want this hardware timestamp, you need the PTP clock, hardware timestamping capability, to make use of that. Okay, any questions?
Hi everyone. So my name is Amr. Amr. I know it's hard to pronounce, but you can call me Amr, Amir, anything close to Amr. I'm okay. I hope you are still awake. I know it's hard to stay for 2 hours on Monday, but I try to be quick. So I will talk about Beagle Bone PRU, which you will use in one of the assignments. I think the coming one. As you know, the IoT requires different level of time. For example, some of them require seconds, microseconds, nanoseconds. So you have to provide different level of synchronization. What we target is time-aware IoT user. What I mean by time-aware IoT user, as Fatima presented, we have this hardware which has a lot of time stamping, registers, all this stuff. We have the kernel, we have the shell and the application, and we have all the way up the user. And now we would like to know what user can monitor all the way up. He will see different accuracy, uncertainty, and stability as he is all the way up away from the hardware. One of the nice embedded platforms is Beagle Bone, which you will use or already used in the class. This Beagle Bone has a lot of nice features. You can add different OS, and you can choose your flavor, programming language, environment libraries. For example, I will pick something Linux, Angstrom, C++, OpenCV, and then end with a cool application. So it supports multiple things. Also, it has a very nice low-level thing called PRU. Fatima already talked about that a little bit. So PRU is programmable real-time unit. This PRU, it has capability of accessing the I/O with 200 megahertz, which means that you can execute which means that one instruction will take 5 nanoseconds only to execute. It has a dedicated instruction and data memory, and it has a parallel. It's like a co-processor, as Fatma said. So you have here the ARM side, and you have here the PRU side. And I will compare between the capability of the ARM side and the PRU side. So let's take a look at this PRU benchmark. At this slide, you can see we are writing here in terms of assembly on the ARM without any Linux. In this slide, I'm targeted to compare the ARM side and the PRU side in terms of capability. So in the ARM side, we are writing as low level as we can. So we are writing in assembly without Linux. And on the PRU side, we are using also assembly, which is the common language. And we are only toggle the pins. As you see on the ARM side, you will be able to do it in 200 nanoseconds. You cannot go lower than that. However, in the PRU, you can do it in 5 nanoseconds, which is 40x faster. So this Beagle Bone is really powerful, as it gives you high-level stuff, as you can both Linux play on top of that, and it also has low-level capability, as you see here. And PRU is used in many applications: audio processing, real-time sensing, and you can check these papers. However, PRU has a very painful process to play with. You will find that you need to write assembly to play with PRU, and you will find that you will have to go through a very painful configuration process. As I said, there is 2 ways: the ARM and the PRU, and you have to say, okay, this pin is dedicated to the ARM side, this pin is dedicated to the PRU side, and this is a painful process for normal users. If you are expert, okay, I'm not talking about you. So I will talk about user space I/O driver, only to give you the big picture. How we can control the PRU from user space. What's usually happening that kernel will have some complex drivers that will facilitate and give you like high-level access to the hardware. So it's like give you high-level APIs, and it will do all the complex stuff underneath. This is way of controlling the physical layer from the user space. There is another way that you expose all the registers to the user and ask him to play with it. So he has then a nightmare to like configure all this stuff. He has to take care of it himself, and this is the case for PRU. Everything is exposed to you, and you have to play with it. The advantage of that okay. So the advantage of that the kernel code is hard to debug, so the software code is easier, or the user space code is easier. However, it's not secure, so anyone can mess up with your code. There is something called UIO press driver. So this is a driver which exposes the PRU stuff to you in the user space. Any question until here?
Does Beagle Bone have a working driver?
Sorry?
No, Beagle Bone has a working driver.
No, I am not sure. I don't know. Sorry. Any other questions? Okay. I hope you are still alive. Your face doesn't give me some.
So you're asking Beagle Bone has DMA? Yeah, Beagle Bone has DMA, direct memory access. I haven't checked it, but it should have. I mean, why wouldn't it have? It's a pretty important functionality in Beagle Bone.
Yeah, there's basically I was trying to do an application where I could get I can replicate it with PRU and on Python days and
How did you do data transfer? From Uspace?
Yeah,
It's part of using DMA.
I knew DMA was here, but there wasn't any driver, and I think I'm kind of doing it right now.
Okay. Yeah, I'll look into it.
Okay. Any other questions? Okay. Also, I would like to talk a little bit about BinMax, which you will deal with that in the assignment. I am repeatedly saying assignment. I feel that people wake up when I say assignment, so you will make use of it. So, you know, the hardware supports multiple functionalities, like can BWM, EDC, all this stuff. And it doesn't make sense to have like a bin, a dedicated bin for each hardware. So what they did, they multiplex the bin. So it has an advantage that you have lower number of bins, but on the other hand, you cannot use all of them at the same time, which is the general case. No one will use all this stuff on the same time. If you need to do so, you have to do your design from scratch or use multiple of them. So the Beagle Bone has something called bin max. That's something like this figure. It's not like that in reality, but it's something like you choose the mode of the bin based on your needs. So you have to make sure that you put the bin on the right mode before you move on. This table is pretty popular in Beagle Bone. If you would like to play with, I think you need to do so in the assignments. I here cut part of the table. You will see here is the bin. On the Beagle Bone there is two sides, B8 and B9. For example, here I am talking about B8, and each bin will have a dedicated address and multiple modes, up to 7 modes. Not all of them will have the seven modes, but some of them will have 7 modes. For example, if I would like to say, okay, please use bin 811 to the PRU 0, I will say something in something called overlay file. I will give it like the address. If you go to the address of 811, which is here, you will see the address is 34, which is here, and then you will say, okay, I need mode 6. So this is like a big picture of how you write the overlay, and you will find a lot of examples online for this.
So is the first line of code the same as the last line of code? Just different ways of doing it?
No, this is the same file. This is one file. You have to specify all of these.
But why does so what does the first line of code do?
It's here you only write the bin name. I'm not sure how they combine the file. I only understand how to use it. So you have to do so and specify here what you will do, what you will use, and here is the address, and here is the mode. Yes. But it's specified for Beagle Bone. It's not for anything else. So all of these only for Beagle Bone. And this table is for Beagle Bone Black.
There is a folder called documentation, and under that we have a data. We can see something like overlay notes and all of them. They're all in the
Thank you. So you can check a lot of examples online, and you will get better understanding. So let's take a look of how PRU think about time. As I said, there is hardware, there is kernel, application, and there is user. And the PRU setting on the hardware side, and the user is all the way up, saying the Linux time, which Fatima described using get time, get resolution. All of this is Linux time, but the PRU is totally hardware time, or like a counter value. So the user will be confused between this. He would like to make use of the low-level capability, but he has another notion of high-level time. So how to solve that? One of the popular examples of using the PRU is the inverted pendulum. I think one of the projects here will end up with building inverted pendulum. I hope they succeed. So for the inverted pendulum, you will have, all of you know the inverted pendulum? Anyone doesn't know what inverted pendulum is? Okay, so inverted pendulum is something that you would like to keep up. And we will connect the inverted pendulum with Beagle Bone. This is the setup in our colleague lab in Santa Barbara. So the idea is they have the controller on Beagle Bone Black, and they have the system, which is the inverted pendulum. All of you are familiar with this loop, control loop, BID. All of you are familiar with it? Okay, so it's a very simple control loop. You have controller, you have system, and now the PRU will come on the picture as you would like to do a precise action with low-level stuff, but you are on the Linux side. So think about this controller would like to take precise action using the PRU, but the user is sitting on top of the Linux side, so he would like to make use of the PRU. I'm giving this example as to motivate using of PRU. Here is a video to wake you up. It doesn't work. Okay. Doesn't work. Yeah. Yeah, only run the video. So here he make use of the PRU to control the inverted pendulum and make precise actions. So as you see, it can stand up, and there is a lot of research showing the effect of being asynchronous, like doing asynchronous action between the control side and the process side. So it's very important to do precise actions and to be synchronous. Okay, let's continue. So you will deal with a framework called Cyclops in the assignment. So the idea of Cyclops is to help you in automating the configuration. You don't need to do all the painful configuration stuff, and it provides like open source JavaScript inspired language to program the PRU. It also has a browser IDE for prototyping on PRU instead of using low-level stuff. It provides some APIs to do some common low-level stuff. There is another way of dealing with PRU. Instead of writing assembly, there is a TI compiler where you write C. However, it has advantage and disadvantages. The advantage that you will not write assembly anymore. However, you will write C with over a closed compiler. So you will use the predictability of the time on the low level. So you will not reach the 5 nanoseconds, which I showed you at the beginning if you use the TI compiler. However, again, it's a C, so it's a trade-off. So Cyclops takes the advantage of both. It provides, yeah.
Why can't you get, if it's C, you just directly like XOR a register or a memory location that maps to a register, and then get converted into assembly? Why would you not be able to get 5 nanoseconds precision? What is the compiler add that makes it?
You mean write assembly in C?
Well, even just a C line. So let's say you have the same register that you're toggling in assembly to make it go up and down. Okay. Toggle in C with just an XOR
but you don't know how the compiler will generate the code. For example, if I say for loop or while something, wait for some time, then toggle the bin, something like that, you don't know how the compiler will do it. Every line of code matters now. You are talking about very precise timing action, 5 nanoseconds. So you don't know how the compiler will do it, and you don't have access to the output also. So you have no idea what will happen. And we will see here an experiment of that as a disadvantage of using the TI. Also in Cyclops, we will be able to do like time synchronization between the Linux side and the PRU. I would like to say that this PRU is out of one of many projects, very talented students, and it ended up in a paper. And also there is another paper out of many classes. There is a lot of papers goes out of many classes. So try to do as good as possible. I mean, a lot of projects has a lot of good ideas, which can end up in a research paper. So do all your best and good luck. So here is the Cyclops IDE. He depends on one of the open source IDEs. Here you can write the Java inspired language, and here you can press compile. You will get the errors here, warning, and here you can see the generated output. And now you can play with the generated output, comment one line, replace it if you don't like the compiler behavior. So as you see, it has a very great advantage that you have access to the output, play with it. So here you have full accessibility to the output of your compiler. This is the Java inspired side of Cyclops. It's not TI compiler anymore. Okay, you got it? For Cyclops, it's only a baby language still. So it has variable assignment, direct reading and writing to bin, arithmetic expression, condition statements, loops. To give you some intuition, don't think this is an easy thing. I was impressed that most of this work is done by only one person in like 2 or 3 months, and all as I said, the PRU is written in assembly, and now we are doing this over a high level language. You know how assembly is painful in programming. Now when it comes to the TI side, we provide also some APIs over the TI side. So for example, if you would like to play with EDC, you can call only this API, and instead of configure it yourself, you can read the EDC, read bin, assert bin, toggle bin, only APIs. And you don't need in Cyclops to configure the device overlay. It will automate the configuration, so you don't need to configure anything. Once you write pin 1 equal 1, it will understand that this pin is used as an output, configure it as output, assign it to the PRU. All this is underneath. Any of you knows how to do time synchronization between two sides? If you have clock and she has clock, how to do time synchronization?
So you can send the communication between the two, right?
Yeah.
So you can send a packet that includes what time you think it is right now. But at the same time, you start your own timer, and then you wait for a response from the other side to get back to you. You timestamp that one as well, and you stop the timer, and you measure the difference between when you sent your packet and when you received the packet back. And the person that sent the packet back has also inside of that packet what time they think it is when they got it. Subtract the difference and add your timer value. Not the most communication that's happening either, right? Because if you have like an indirect communication, that wouldn't work anymore. When you send the person, then it doesn't keep moving. So remember, if you want to delay
Yeah.
things that you said was also right, and you also have to take care of the propagation delay, the time the packet spent in the medium, starting from you to the other.
I have only one comment on your and how you describe it. You are not calculating the offset between sending and receiving. When I'm talking about time synchronization, I would like to know if I am saying 1 p.m., what's 1 p.m. correspond to your side. For example, if I say to you, what's time in UTC, how you can transfer this to like BDT, GMT, anything. This is time synchronization, that you understand the offset between the two time entities. Okay, so this is the big goal of time synchronization. Now, how to do it? This is my question. There is multiple ways. The easiest way is to do only one message, like this. For example, this is the master node. Well, the time at the master node is 3 time. For example, time equals 3. And he will send to the nodes, okay, my time is 3. Now, every node will build a table. What's my time at 3? Now, this node, its time is 15. So now, repeat the process. You will have a table of mapping. Now, use some functions to map from this time value to this time value. The easiest thing to calculate the offset, okay? The offset between them, the offset between them is 12 or something, and add the offset, and that's it. So you need to calculate the offset between the two nodes, not the offset between sending and receiving. However, to clarify, when people need to do two-way, if you need to do two-way, you are talking about calculating the propagation delay. As I expect from you when I describe this process, to say to me, okay, 3 is not corresponding to 15, as there is propagation delay time, right? Do you understand this? What time synchronization? It's like a time stamping a common event on the two sides, right? Yeah, propagation delay, you need two-way. You need two-way messaging, and there is a very popular formula to calculate it. Only take the offset, as he said, something out of it. I can post it to you. So,
would also cover in his class about clocks and time.
Yeah, I think there was a lecture about that.
He said he hasn't given it yet.
Oh, okay. Yeah, so in order to calculate the propagation delay, you have to reply back. And you will have now 4 time stamps. Receive, send, receive on both sides. Now you will be able to calculate the propagation delay. However, a lot of people assume the propagation delay is constant, and they will deal with this structure. So I receive it at some time, take out of it a constant value, and then play with it. Now, why I said that, as I like to describe how we do the synchronization of PRU with a Linux type. So the big picture of time synchronization, you have 2 entities, and you would like to know to timestamp a common event on the 2 entities. Are you still awake? No? Okay. Okay, let's see. So we have PRU, we have the ARM side, we have kernel on top of the ARM, we have the user space on top of the kernel. And now we would like to synchronize this guy with the PRU. So we will connect physically one pin from the PRU side to the ARM side and assert this pin. This is like a common event. So what do you expect me to continue? What do you need from me now to do time synchronization, given that I will do this assert pin? Can anyone guess? What's time synchronization? Any idea? No, don't talk about how you will do it. I'm talking about, I would like to synchronize 2 entities, and there is a common event. I would like to continue now in describing. What do you expect me to do now? I said to do time synchronization, you need to do common event and time stamp it on both sides, and then do calculation to match them, right? So what do you expect from me now? Any idea? Phone? Say whatever. Manny is not here. However, he can say the recording. So what do you think? So I would like you to get the big picture of time synchronization. If I ask you to do time synchronization between two of us, how you will do it? Exactly, you need to timestamp a message on both sides. So now this is my common event. I expect to get the time of this event here and the time of this event here, and do the mapping. See how simple it is, right? Yes? Okay, let's see how to do it. I now assert the bin from the PRU side to the ARM side. The PRU will read the time. Of course, it's not accurate as it executes every 5 nanoseconds. So you already lose some time here. Then the PRU will convert this value to nanoseconds. As Fatima said, you are reading a counter value. So you need to map the counter value, deal with overflows, and map it to nanoseconds. Now the PRU is done. Let's see on the ARM side, which is a scary side as it has ARM kernel user space. You will find that the ARM has some low-level capability to capture the time. Low-level capability, it means when I toggle a bin, it can take a copy of the counter in hardware. So it will capture the time, send it to the kernel. We have here kernel module that converts this value to a nanosecond. Then we will send this value to the user space. Now the user space will send back this T4 to the PRU. Now the PRU has two values, the T4 and the T2. Now it's the two timestamps of this common event. Now the PRU can get and adjust the time. Anyone understand anything? I mean, if I tell you the time now is 1 p.m., you can add to it and do some calculation to get the time on the other side. So if I tell you 1 p.m. at GMT, can you calculate the time at UTC? If you can, now you have the transfer function of time synchronization. So yeah.
So if they have a delta, so let's say you have two parallel clocks running, and one thinks it's 1 p.m., one thinks it's 1 p.m. 1 minute. So they have a 1 minute delta. That's what you're trying to correct here, right?
Yeah.
Okay. So you would basically not only timestamp that, but read whatever the timestamp of the other side is, which is contained inside of the packet, right?
Yeah.
Okay.
Yeah.
In this particular case, there's no packet exchange. PRU and ARM are on the same platform.
Oh.
The common event which we are generating is that we connect two pins. One the PRU pin, ARM pin, and they both are getting a common signal, an external common.
But there is still this is a message exchange between the kernel and the PRU side, right?
Yeah, same platform.
Yeah, it's on the same chip, yeah, but they are two entities, right?
So, like, how do you send is it a one-bit message then? Or is it just a one pair?
There is a kernel module that play and let you send from PRU to Linux, and you will play with that in the assignment. So it will let you deal and send and receive messages. Any more questions? So this is like the architecture of Cyclops. The blue parts is for the Java-inspired language. You will see here is IDE, here is PRU, and some stuff in the user space, some stuff on the kernel. The red boxes are for the TI compiler. This is the UIO driver, which I talked about, to expose all the registers of the PRU all the way up to the user so that he can play with. So let's take a look of how to generate pulse width modulation using PRU. This is the original language of PRU, which is called Bazel. You will write some assembly and configure everything by your hand, write the overlay file, all this stuff, compile all, do all this stuff. On the other side, you can do this with Cyclops in the C library using the API, like assert pin, wait, deassert pin, and that's it. And here, he will understand that you will use this pin as an output. You don't need to configure anything. If you use the Java-inspired language, also here you can set the pin to something, and he will understand it's an output and automate the whole process for you. You don't need to configure anything. And the tick here is like the counter tick. Wait for some time, then toggle the pin. This will generate some pulse width modulation, up high, with some width. Okay, I would like you to tell me how to evaluate time synchronization. I assume that you understand how to do time synchronization. Now, if I claim to you that I have 10 microseconds time synchronization, how you can evaluate me?
So you can have them both at a predetermined time, have them both toggle a pin high, and then have the two pins coming out in the oscilloscope, and you can see when they both go up and see how different they are.
Okay, this is
if they're truly accurate, they'll both up at the same time. If not, they'll get slight delta between them.
Okay, this is one way. Anyone would like to suggest another way? You would like to suggest? So what he said, can anyone repeat what he said? Come on, guys, I have finished, so only repeat. So do you understand what he said? So what he suggested?
At a predefined time, like you decide that both the processors are going to give out a particular event, trigger an event at a particular time, and then you observe if both the processors are triggering the event at the same time. And if there is any delay, then it's present delay. Otherwise, they are accurate.
Okay, so in other words, he is saying we agree to generate an event at 5 p.m. and then on an oscilloscope see the difference. Okay. This is one way of evaluating the time synchronization. Can anyone suggest another way?
Compare the timestamp of a bunch of events and see if they have the same.
Yeah, can you explain more?
If you have events that's occurring on both processors, you just, like the whole picture, you just look at the timestamp, and if one's 11 and one's 15, then they're not.
Exactly. So this is another way. Yeah. Exactly, yeah. So what Liam suggested, to have something monitor the input to the output of the system, like do something at 5 p.m. But what he suggested, so what's your name? Jay. So what he suggested, to have someone monitor the input. So I will do events, you will tell me the time, he will tell me the time, I will compare. So this is two ways of evaluating the time synchronization. Here, what we did, we generate an event on both sides. So we used your idea of generating a common event and compare the time between the two sides. And this is the synchronization error. It's in microseconds between the two sides, given that the synchronization period is 32 seconds. So every 32 seconds, I will repeat the whole process of exchanging the timestamps. Or why I repeat the whole process? Can anyone guess?
So oscillators aren't perfect and will drift. Then you gotta keep.
Exactly. The clock are drifting. There is a lot of environment factors, so you need to repeat the process. So you would expect if I repeat more, I will be more accurate until I saturate to some level. Here, if we do the synchronization once, you will see it's worse than before, which is expected, as when I do more, I will be in a better shape. This is the latency for doing read PRU time. So read PRU time requires 600 nanoseconds, and adjust PRU time requires 2 nanoseconds. Read time requires 115 nanoseconds. Now I give you the answer. Let's return back. I expect any of you asked me why you didn't get perfect synchronization. You are on the same board, claim that you are a great person using PRU, Superman, and now you are talking about microseconds, not nanoseconds. Can you tell me why? Why it's not nanoseconds accuracy? First, do you understand this figure? All of you understand? No? Okay. You already said the idea and you didn't understand this. Okay. So I generate here a common event, and the PRU, one bin is configured. Yeah. So one bin is configured to PRU, one bin is Linux side, and then both of them will timestamp and to do time synchronization to compare. And this is the synchronization error between the two sides. Okay, so my question now, why it's not 0? Why it's not nanosecond? No, it's not 0, it's microsecond. When you are talking with time people, microsecond is bad. No, it's 500 nanoseconds. Yes, but it's not nanoseconds, it's microseconds order. This is how you can fake people in writing papers. You can write nanosecond and then suddenly on the scale write 1000. It's not nano, actually it's micro. I mean micro order of magnitude, not nano. Yeah, why it's not 0? Yeah. Yeah. Yeah, listen this. How we do time synchronization? Again, let's repeat to the original problem. How I do time synchronization? I will do an event. I will tell you this is my time, this is your time, and then we will compare. So when I tell you my time synchronization is not perfect, so what do you expect? There is a problem in this process of generating and comparing time. When I generate, am I accurate in generating? And when you capture, are you accurate in capturing? And when we send, is there a delay in sending? This is all the sources of problems in time synchronization. And I already cheat you and give you some hints, and no one take it. I'm telling you, this is the delay in doing the APIs of reading the time, adjust the time, read the time again. All this stuff has a lot of latency, so it's not accurate. It's not fixed. It's like mean. So did you get an idea why it's not perfect synchronization? And now return to Leon's question. This is over the TI, which is a closed compiler. So we don't know why it's such a huge latency, as it's a closed compiler. I hope someone of you like Cyclops and do it on the Java-inspired language. I am sure you will get much better than these results, as these results over the TI compiler. Do you understand?
I have a question. So if it's a closed compiler, does that mean you can't read the assembly output that it generates?
Yeah, you don't know what's going on. What?
You still read the assembly output?
No, I don't think you can see the output. It's like binary. Do we have time? Little bit. Let me show you the Cyclops repo as you will play with it. I will open. I don't think so. You can see the binary only.
Right.
I am not sure if it's possible to do so or not. But also, I am not sure if the result will be readable and you can modify it.
There will be support, for common binary formats like ELF. There are tools for converting binary to max.
Yeah, maybe if you consider extra process like that, you may get better result by enhancing the output. But here we are using it as a black box. We didn't modify the output. We just depend on the output, write as clean as we can on high level, and that's it. But you can consider clean it more. Do you got my point? You understand? I'm talking to you. Yeah. Yeah. Guys, can you be quiet a little bit, guys? Can you be quiet? We need to hear him, right? So you are saying that there is a problem, and yeah, I'm saying you don't know what's going on. We just depend on the output, run it, and that's it. So we didn't consider try to hack it and see what's the assembly, fix the assembly, all this stuff, see where is the source of error. Yeah, we didn't do that. You can play with it, inshallah. Yeah, we treat it as a black box. So in the assignment, you will play with this Cyclops. It's under the Nestle. I think Professor Manny will post for you the slides, so it will have the link. You will find here 3 folders. The C library folder, and it has examples to play with if you would like some hello world examples. There is a Java-inspired side, which is the IDE. It has some instruction how to run it, all this stuff. And there is a full image if you would like to build an image, as this work is only compatible with one kernel. As you know, Linux has a lot of messy stuff. If you change the kernel, a lot of stuff will change. So this work is only tested on one kernel. So we recommend to use the same version and the same image. Fatima, where is the slide? The slide deck? What is it? Okay. So these are the references for the presentation and some figures that I borrowed or stole. And thank you for your time, and send us. Thank you guys. Send us messages. Our emails, I think, are on NISL website, so you can send us message whenever you want. Thanks for listening.